Hello, I'm Sanziana Foia from the CCDC, and today we'll explore together optical isomerism and chirality, starting from something you know as well as the back of your hands. We will see everyday examples of chiral objects and how that affects their properties and behaviors. Then, we'll step into the microscopic world and learn about chirality and optical isomerism in molecules and visualize it in 3D. Let's get started. In chemistry, we often hear about the term isomerism, referring to molecules that have the same formula but are arranged differently in space. There are multiple types of isomerism, such as position, functional, and geometric isomerism, to name a few. But perhaps one of the trickiest to get our heads around is optical isomerism along with the notion of chirality. Let's take a quick break from chemistry and take a look at our hands. What do you think? Are they really the same? They're both made of the same stuff, a palm, a thumb, and 4 other fingers, and they both have the same bones, muscle, and skin. And that's not everything. Not only are they made of the same stuff, but the shapes, sizes, and distances between the stuff that makes them up are all the same. Now try superimposing your hands. That's just a fancy way of saying to lay one over the other. No matter how hard you try, you can't perfectly fit them one over the other, say, in the same way you could do with 2 left hands from 2 different people. So there must be something special that makes your hands different, despite the appearance of them being identical. And that special something is called chirality. Chirality, or handedness, is a spatial property of some objects, such as your hands. Put your hands together and notice how your left hands look like it's looking in a mirror at your right hand. Your hands are mirror images of each other. Objects that are mirror images of each other behave differently in space. Take screws, another example of everyday chiral objects. By screwing a left-handed screw to the left, it inserts into a wooden board. But if we twist left a right-handed screw, it will come out. The same action can have opposite effects on objects that are mirror images of each other. Another example is kitchen or even boxing gloves. The left glove won't fit onto your right hand, no matter how hard you try. Chiral objects have different spatial properties and often behave differently. But how does all this apply to chemistry? Take a look at the 2 molecules you see here. Each one has a central carbon atom bound to 4 different groups: a hydrogen, a methyl, ethyl, and a chloride. Just by looking at what they're made of and which bonds they form, they appear to be the same. However, if we try to overlay the 2 molecules by rotating and translating them as we wish, we'll see that no matter how hard we try to move them, we can never perfectly superimpose them. Try and build a 3D model of this molecule to convince yourself. Feel free to use materials you have around the house. You can even try toothpicks for bonds and various fruit for the atoms. Just as screws or your hands, molecules which appear identical at the first glance are also chiral. They have the same components and the same internal distances between these components. However, on closer inspection, we will notice they are in fact mirror images of each other. Stereoisomers don't only differ through their arrangement in space. They often have different properties and behaviors, as we've seen with hands and screws. Take carvone, a molecule found in cumin, toothpaste, and spearmint. This is the chiral carbon in carvone. Don't get confused by the 6-membered ring. The chiral carbon is attached to 4 different groups, even if 2 of them are joined in a ring. As you can see, carvone has 2 non-superimposable stereoisomers which have different chemical properties. One has a strong spearmint smell and is used for flavoring mint sweets and toothpaste and can also be used as a mosquito repellent. The other stereoisomer is present in cumin and other spices and smells of caraway. It can be used to prevent potatoes sprouting during storage. We've seen how chiral molecules behave and learned their importance in chemistry. Now let's see if we can recognize which of the following carbons are chiral. This molecule is alanine, an amino acid. Can you guess which of alanine's carbones is chiral? Remember, a chiral carbon has 4 different groups attached to it. Feel free to pause the video if you need more time to think. The right answer is B. This carbon is attached to 4 different groups: a hydrogen, a methyl, a carboxylic acid, and an amine. What about this molecule of citric acid? Can you identify a chiral carbon? That was a tricky one. Citric acid has no stereocenters. Look carefully at the structure. There are no carbon atoms that are bonded to 4 different groups. Did you know that the molecule of ibuprofen is chiral? Which carbon do you think is a stereocenter? That's right. The correct answer is carbon A, which is attached to 4 different groups. Now take a look at these stereoisomers of thalidomide. Thalidomide is a drug that was prescribed to pregnant women to reduce the effects of morning sickness in the 1960s. The drug was sold as a mixture of the 2 stereoisomers, only one of which had the desired effect against morning sickness, while the other led to many disabilities and deaths in babies. This shows just how important it is that we can correctly distinguish the isomers of chiral compounds. Can you identify which carbon atom is a stereocenter? Give it a thought before I reveal the answer, and feel free to pause the video if you need more time. Great job! Thalidomide's chiral center is this carbon with 4 different groups attached to it. Don't worry if you didn't get it right this time. It takes more practice to rapidly identify tricky stereocenters such as this one. Congratulations! You made it to the end of this video. Today, we learned about optical isomerism and chirality, starting from something as simple as our hands and all the way to the fascinating world of chemistry. We saw how some objects, be they gloves, screws, or complicated molecules, can be different from each other despite being made of the same components which are connected in the exact same ways to each other. If such objects can't be superimposed, it means they are far from being identical. They're mirror images of each other. We then saw how chirality can have a major impact on the behavior of molecules such as carvone or thalidomide. And finally, we challenged ourselves with identifying chiral centers in various molecules. If you enjoyed learning with us about optical isomerism and chirality, give this video a thumbs up and subscribe to our channel for more educational content. Don't forget to check out the teaching modules linked in the description below. Thank you for watching.